Hello everyone. On this video, we're going to talk about one of the most important fields in computer science, which is graph theory. Graph theory started as a riddle in the 18th century city of Königsberg, which is now known as Kaliningrad. The city is run through by the Pergola River, which divides it in four distinct land masses and are connected by seven bridges. One of the most famous puzzles at the time, which was usually asked around the time, is can you go through the four land masses of the city, crossing each bridge exactly once, and ending up where you started? Now, this riddle was answered by the famous mathematician Leonhard Euler, who, instead of thinking in terms of geometry or geography, thought about an abstraction of the city. He focused on connections, and so he replaced each landmass by a simple point, a vertex, and replaced each bridge by an edge joining the two vertices. And by doing so, he modeled the city as a sort of a graph, and that's what we call that now in mathematics and computer science. Now, graph have a mathematical definition, which is it is a pair of two sets, a set of vertices and a set of edges. And each edge is just a pair of connected vertices. Now, sometimes an edge is ordered, sometimes the order is important in an edge of vertices, and in that case, the graph is directed, which means if you have an edge I and G, it matters if the edge starts from I or starts from G. However, there are also sometimes it doesn't matter. An edge from I and G implies an edge in J and Y, and that graph is what we call non-directed graphs. Now, there are other several definitions about certain properties of graphs. For example, an order of the graph is the number of vertices, and the size of a graph is the number of edges. But one of the most important definitions in a graph is the degree of a graph, which is defined by the degree of a vertex. A degree of the vertex is simply the number of, we say intuitively, it's the number of neighbors of a vertex, but it's also the number of the incidence edges in a vertex. How many edges are connected to the vertex. Now, the degree of a graph, or the maximum degree of a graph, is the largest degree of among its vertices. And it is very important because we usually use the degree of a graph or the degree of vertices to prove so many properties and theorems about graphs in general. Now, graphs are very important because graphs are used to model any system that is modeled by any data structure that is that contains connections can and is usually modeled by a graph, whether it's social networks, web pages, transportation networks, circuits, and even in video games we use graphs to model maps of 2D and sometimes even 3D video games. Graphs are very important. Now, back to Königsberg. The characterization or the property of being able to go from one landmass and visit every bridge exactly once and then end up either at the where you started or end up elsewhere. Since Euler answered the problem, it's named after Euler. When we call that property is whether it's a Eulerian path or a Eulerian circuit. If you end up where you started, it is a circuit. If you don't, it's a path. And a Eulerian path is not it can be a circuit, but it doesn't go that way. Now, obviously, not every graph is such a graph or contains such a path or circuit because there is a characterization that Euler came up with, and it's a simply easy characterization with which we prove whether a graph is a Eulerian or not. The idea is simple. Now, for each landmass, to be able to go through a bridge exactly once and end up where we are, it needs to be that for each landmass, the number of bridges connecting to that landmass where in your path or circuit you end up on that bridge, you end up on that landmass, the number of bridges that let you arrive at the landmass should be equal to the number of bridges that let you outside of that landmass. This would work if this would be easily understandable if you think of the path being ordered, even if the graph isn't. Now, since the graph isn't ordered, isn't directed, I mean, there is another way of looking at it. If the number of bridges taking you inside a landmass is equal to the number of bridges taking you outside of the landmass, that means that the number of bridges connected to this landmass should be an even number. And now going back to the model realism, to the graph, this means since each landmass is represented by a vertex, that means each vertex should be connected to an even number of edges, which represent the bridges. And that means, as we have defined, it should have an even degree. This is necessary if you want to have a Eulerian circuit and end up where you started. Because each time you go through a bridge, you end up on another landmass, and you keep going until you end up on where you started. Now, what if we're talking about just a path, not necessarily a circuit? You may start on a landmass and end up elsewhere. This is possible if the starting point and the ending point have one. The starting point has one bridge that takes it out, and then the ending point has one bridge that takes it in, and that means for the starting landmass or the vertex and the ending landmass or the vertex, they should have an odd degree for the in bridge and the out bridge. And to have that, you need only the starting and ending point to have an odd degree. And so it should have exactly two vertices of an odd degree. Now, if there are more, you no longer have the Eulerian path. If you no longer have the Eulerian path, you no longer have the Eulerian sequence, and the graph is not Eulerian and doesn't respond to the riddle. Well, this is a simple method that we can use now. What was a very famous riddle can be now answered simply, and this is the beauty of mathematics. Now we have the representation of the city of Königsberg as in a graph form. You have four vertices for the land masses and 7 edges. As you can see, D has an odd degree, S has an odd degree, but also N has an odd degree, and that means you cannot have an Eulerian path here. So no Eulerian path, no Eulerian circuit, and so the graph is not Eulerian. And this is how I understand now that the answer to the riddle is no, you cannot have this walk here. You cannot answer the riddle that way, and that concludes the riddle. Now, I've said before that graph theory has a lot of applications in software engineering, systems engineering, and also now in AI with graph neural networks and whatnot. But how it's easy to intuit the data structure of a graph when we're doing it mathematically, formally. But what about representing it in a machine? Now there are two ways to represent a graph in a machine or a computer. The first is an adjacency list, and the second is an adjacency matrix. Both of them are very, very useful, very important, but the use depends on the graph itself. I will explain how. Now, for the first representation, which is an adjacency list, it's basically a list of lists, and the size of the adjacency list is the number of vertices in the graph, and each list inside the adjacency list is just a list of the neighbors to represent each neighbor of each vertices. It's very useful when you're trying to represent graphs that are sparse, when there aren't many connections, and the graph is not very well connected and it's not dense. It's very sparse. A graph, an edge list is important and very useful. The other type of representation is the adjacency matrix. An adjacency matrix is, for example, if the graph is of order n, if you have an n number of vertices, you use an n times n matrix. Why is that? Is because basically for each two vertices I and G, you just look at the coefficient of the matrix in the I and G place and see if it equals 1, you have an edge. If it doesn't, it doesn't. If it equals 0, you don't have an edge. This is an adjacency matrix is very efficient when you have a very dense or very well connected graph. It takes a lot of memory. It uses O(n) to the power of 2 memory, but it's very useful if the graph is very dense, and it's better not to use it if the graph is sparse. Now, it's easy to test adjacency. It's easy to check to test the adjacency, as I said. Also, if the graph is undirected, the matrix is symmetric, so you can use a reduced form of the matrix with the orthogonal decomposition. Also, if the graph is sparse, you can use, and it has a lot of zeros, you can use a reduced form of the graph using a decomposition like singular values decomposition or any other mathematical decomposition of a matrix. This is why linear algebra is very important in graph theory, and graph theory is also important in its applications in deep learning and AI in general. Now that's it for today. Next time we're gonna explore how to traverse or search through a graph and the methods used, which are very useful to decide if a graph is Euler, but also to find the shortest path and all of that. Thank you very much for watching.